Well, a very, very warm welcome and a good afternoon to everyone, and welcome back to our second week of the Summer 2022 Bite-Sized Corrosion series. We've titled this current series as Hidden Dangers of Cathodic Protection. And you may recall in our very first session together, we talked about how we can categorize some of the dangers associated with cathodic protection into physical dangers. We called them consequential or electrochemical dangers, and even social dangers. And you'll recall, if you joined us last week on Wednesday, that we spent time with Diana Katsky, and she and I had a fairly sobering discussion about vandalism, which in a sense is a social danger associated with cathodic protection, and one which I think we need to perhaps spend some more time exploring and trying to be creative in our solutions. But that's not today's topic of discussion. Today, I think it would be a good idea to explore some of the dangers or the risks that are associated when we have too much of a good thing, in that when we turn up our cathodic protection too high, we can have some challenges. Now, it's wonderful that Neil Webb is able to join us, and we're hoping that he'll be able to join us for the whole session, because Neil has come to the mic from the Kruger Park. Neil, tell us where you are and what you're up to.
I'm not quite in the Kruger Park as I'm speaking. I'm at a timeshare just outside the park, but we, thanks to Wildcard, are able to pop in and out of the park at will. And we had a really great quick visit on Saturday when we arrived, with a mixed herd of grazing zebra and impala being scared off by a pack of wild dogs, and they went hurtling past us at a great rate of knots, and lo and behold, there came one of the dogs hurtling past us, and I was able to snap this photograph. But the advantages of technology mean we can sometimes really enjoy our country at the same time as doing some work.
And we're going to be talking about cathodic protection and when we turn it up too high. And one of the risks, Neil, we know that cathodic protection requires current. And obviously, just from a resource saving perspective and corrosion control perspective, we want to try and optimize the use of current that we apply to our structure. Perhaps I should say not apply too much, but what's your perspective on how much current is enough and what we're applying to our structures?
Well, of course, as coatings have improved over the years, the current requirement to achieve cathodic protection has steadily decreased. And the result of that is that the effective insulation value of the coatings has meant that the pipelines are becoming more and more susceptible to AC interference. Mm-hmm. And we need to remember that the primary source of interference from AC power lines when they are running parallel is that of induction. It's an electromagnetic induction, and therefore the power lines induce current in the pipeline. When the coating resistance is low, as was the case with the old bitumen coatings, for example, then that current that was induced in the pipeline would be dissipated without doing any damage. However, with the increase in the use of common servitudes, like this one, I'm standing on a pipeline servitude, taking this photograph of the power lines on each side of the pipeline, and there's another new pipeline being constructed on the far right-hand side. And the net result of this is that the current that is induced in the pipe then has no means of escape, if I can call it that, with a high integrity coating. After all, we have buried cables running at 132 kV. That power doesn't escape, it stays within the cable. So the problem with our pipelines comes with defects in the pipeline coating, and the AC current that is induced in the pipeline then attempts to leave to earth through defects in the coating. And the net result of that is that we can get current actual AC corrosion taking place at very, very high current densities at these locations. Now, here we're not talking about the shock hazard, but rather the corrosion hazard that results from the discharge of AC current through defects in the coating.
So essentially, Neil, there's almost a concern that our coatings are now too good and maybe we're not seeing the real potential on the pipe?
Well, the interesting thing about that is that to a large extent, the AC corrosion is independent of potential as we look at it from a cathodic protection point of view. And in fact, can be counterintuitive in that high cathodic protection potentials can cause or exacerbate corrosion due to AC. And that's really what the primary topic of today's hidden danger. But the question about how do you monitor these potentials is actually a completely different topic that we need to explore someday, because a lot of people reckon that with these very high integrity coatings, what we're doing is measuring the remote potentials of, say, the magnesium anodes, if it's a sacrificially protected pipeline, or the remote potentials of the rectifier, and we're not measuring the reality of the pipeline itself at all.
And that's quite a concern. I know we're going to get into it a little bit more, but right now that implies that we're probably operating our CP systems almost blind.
Yeah, in many ways we are. And in that regard, the use of coupons is a subject for another day.
In fact, it's almost like that's a hidden danger in and of itself, is that we don't know what's going on. But you're right, we'll talk about that another time before we open a can of worms that we can't get them back into. Neil, when we chatted with Craig Werter, we did sort of brush on this concept of the AC and the CP kind of, I want to say, negatively or deleteriously affecting each other. And when we've got all this AC, what are we seeing and how do we deal with it and how do we get rid of it?
Well, what's been discovered is that if your current density on an exposed metal surface is in excess of 30 amps per square meter, and I mean that, amps, not milliamps, amps per square meter, then you are at risk of AC corrosion. So there is a typical defect in a high insulation value coating. It is in the order of a square centimeter, which is has been discovered to be about the most susceptible size of defect in terms of AC corrosion. And you may say, well, how on earth do we get that level of current density? We're used to talking about milliamps a square meter and microamps a square meter when we're talking cathodic protection. And of course, those current densities are in fact the effective current density over the entire pipeline surface, as opposed to the current density on the exposed surface of a defect. And this subject is addressed very comprehensively in the ISO standard 18086. And for somebody to just go and have a quick read of that standard, I'm sure they will end up being totally confused, because it says that, well, if you've got AC on the pipe, you can control corrosion by reducing the level of AC, or you can control it by reducing the level of cathodic protection, or you can control it by increasing the level of cathodic protection.
Which you just contradicted yourself.
If that doesn't boggle your mind, well, then I don't know what will.
So Neil, yeah, I think you better take us through this, because you've just said increase and then you said decrease, and we'll say confused.
It is very, very confusing at first glance. And just to put it into perspective, that's 30 amps per square meter of surface. If you reduce that down to the size of that little defect, the 1 square centimeter, like your fingernail size, that we're actually only talking about a current of 3 milliamps.
Right.
That is the current that's drawn by an LED. So
And
if
we
you,
almost think of that as insignificant.
yeah, exactly. So if you've got that level of current discharging through a defect, and you don't have the correct balance between the cathodic protection and the AC system, you can land up with corrosion. And that's what this little diagram is indicating. Zone 1 is an area where the level of cathodic protection is low in terms of DC current density. Zone 2 is an area where the level of cathodic protection is high. In both of those, you don't have corrosion. Level 3 is where you take the cathodic protection and add AC to it. And you've got the zone in the middle where you can get some quite serious corrosion. Now, that's quite difficult to grasp the implication of this graph. So also in the standard, we have a more easily understandable graph where it plots the AC voltage on the left-hand side and the DC voltage, in other words, the cathodic protection level, on the x-axis on the bottom. And you can see on the right-hand side of that graph, number 1 over here, is an area where you have very low levels of cathodic protection, and up to 15 volts AC, you don't have any issues.
What do you mean by low levels of CP, Neil?
Well, if you look at the bottom axis, we're talking about minus 1.2 volts or less. In other words, less negative than minus 1.2 volts to copper sulfate with the cathodic protection system operational. In other words, an on potential. And that's the sort of values you get with zinc sacrificial anode systems. To try and control an impressed current system at that potential is quite challenging, particularly also if you've got interference. So interference from rail systems, where we've always concentrated on controlling the discharge of current. Where that current is picked up by the pipeline, we can get very, very negative potentials. Well, let me give away my age. Think back 35 years, where some of the pipeline networks were running at minus 25 volts as a result of straight current interference.
And thankfully, ignorance was bliss, and AC, the knowledge and understanding of AC corrosion was less of a field of science, and the coatings weren't as good. So
the other thing, of course, is that those pipelines also just ran straight across country. They weren't restricted to sharing servitudes with power lines like we are with new pipelines these days. Then, if you go to this zone 2, this is an area where the cathodic protection levels are quite high, so minus 2.5 volts. But if you now look at the AC scale, if you go here to 4 volts AC, which is a fairly common limit that is used for low resistivity soils, and you trace that number back to here at about minus 2.4 volts is the minimum cathodic protection level you need. If you are in the range of 1.2 to 2.4 at 4 volts AC, you are at risk of AC corrosion.
And that's probably where the majority of our cross-country pipelines are sitting.
Yeah, quite likely. Yeah. The other thing that is very interesting about this is that with cathodic protection, we go to great lengths with DCBG surveys to identify defects and repair defects down that are above a certain value, because we want to ensure that the cathodic protection is working. The challenge is that as the defect sizes gets smaller, the AC current density gets larger, and the risk gets larger. And that is because the AC current density for a given AC voltage on the pipeline is related to what is called the spread resistance. The spread resistance is the contact resistance between the pipe at a defect and the surrounding soil. And that the formula for that is linear with respect to diameter. Okay, so it's a very simple formula, rho over 2d, rho being the resistivity of the ground. And so as the diameter of the defect increases, so the resistance decreases, and vice versa. The current density, on the other hand, is in amps per square meter. So it is related to the square of the diameter. So as the diameter of a defect decreases, the corrosion risk increases from an AC corrosion point of view. And that is why we find that this relatively small defect of 1 square centimeter is in fact perhaps the most susceptible defect size. And we need to think or pay a lot of attention to the fact that our cathodic protection levels, firstly, and our AC levels are well controlled if we have gone to great lengths to reduce the number and size of defects that are left on a pipeline.
So Neil, talking about control, just a question that's come in, which rephrases what I was about to ask is, so how do you control your cathodic protection and your AC when you've got two pipelines running adjacent to each other? One is old and one is new. So you've got, let's say, for example, in that photograph you showed earlier where you have, you mentioned a new pipeline being installed. So you've got an old pipeline, a new pipeline, and the power lines. And how do you control it and balance it on those two pipelines?
Well, one of the most important things in a situation like that is cross-bonding between the pipelines to ensure that the two pipelines are balanced in terms of one another. But the interesting thing about that is that the new pipeline in that context will act as almost as a feeder, a current distribution feeder, because it will tend to carry the current in the pipeline because of its good coating. The old pipeline will tend to discharge the AC uniformly along the line. So the combination actually works quite well in terms of keeping a system balanced. But you've got to be careful about how you design the CP, how you design the AC mitigation, and so on. It's got to be that you've got to take both pipelines into consideration in doing that. You can't assume that your current requirement for CP is going to be based on the old pipeline, and the AC is going to be largely controlled by the new pipeline, but it will have been discharged by the old pipeline. It's an interesting thing. And there, the use of coupons and control mechanisms, one of the common control mechanisms in that situation is little and often. In other words, instead of trying to put in whacking great big rectifiers at large distances, you put in smaller rectifiers at fairly close to each other, or you even go sacrificial.
And of course, you mentioned coupons. I suppose the standard of the 1 square centimeter coupon has, I don't know whether it arose from this ISO standard or whether the ISO standard acknowledged it. Obviously, the research that's happened to identify that your 1 square centimeter is your greatest risk makes that as your coupon size a very sensible choice.
Yeah, the 1 square centimeter, as far as I know, is nobody yet quite knows why the size versus intensity graph bottoms out or peaks out at that size, but it is what has come out of experiential data so far. And for that reason, AC coupons generally are 11 millimeters diameter, which is 1 square centimeter, whereas DC coupons tend to be larger, typically 10 square centimeters. And then you put typically a 10 ohm resistor in the AC coupon, because your AC coupon resistance to earth is in the order of 100 of ohms or hundreds of ohms. So a 10 ohm inline resistor is not a big source of error in that measurement. And then you can measure the current to an AC coupon, as well as the AC voltage associated with the coupon. But it's certainly pointing to the requirement, as we go to better and better coatings, the big requirement really is in monitoring and control.
And I think also we mustn't lose sight of the fact that this is a fairly new science. And as more research happens, as more empirical data becomes available, we may find that, we're not right. And in future years, they might shake their heads at the way we've approached it. But at the moment, it is what we have found so far to work best. And I think that's sometimes something that we don't think about.
Here is an example of a pipeline operator who thought this pipeline was well protected. They were looking at it purely from a DC point of view. And the intelligent pigging then picked up this metal loss, which turned out to be an AC corrosion phenomenon.
And again, I think because we've not had this on our radar for as long as we've had CP issues on the radar, we find ourselves surprised. And as you say, they think that their system is adequately protected, and then are justifiably horrified when there is metal loss, and depending on the fluid, that might need to be reinforced or replaced, which is also a concern. Neil, a question, and I'm not sure we can answer it, but we can certainly give it a bash, that's just come through, is which coating would be preferable when you're dealing with AC? So if AC is your primary concern, is there a modern coating which is preferable to others?
Well, I'll give you the American answer first, and that is fusion bonded epoxy, because the Americans believe that fusion bonded epoxy as a standard coating is the bee's knees, in that when it breaks down, it lets you know that it's breaking down because it then requires more current. We don't have much in the way of standalone fusion bonded epoxy in South Africa. Of the coatings that we have, believe it or not, the electrical characteristics of all the coatings that we have are very, very similar, be it polymer modified bitumen, 3-layer polyethylene, 2-layer polyethylene, rigid polyurethane, tape wrapping, viscoelastics, whatever it is, they are all high insulation value coatings these days. And unless we go back to blown bitumen, which you can't get anymore, you're actually faced with the problem. It's not going to go away.
Right.
About the only coating that's not an issue with AC is cement mortar sheathing, which is extensively used in Cape Town by the Cape Town municipality. That is their standard coating system. And it's one of its great advantages is that it is not susceptible to AC interference, because it's actually a conductive coating. But then you go and put that on a pipeline in KZN, where there's an Umgani water line that is concrete sheathed, and that has interference currents of hundreds of amps, because it's a relatively conductive coating. So you can't have more.
That's, in each situation, I think we need to bear in mind that it's 6 of one, half dozen of the other, and often solving one problem creates another, and then a good risk analysis will determine which is the best situation in your particular scenario. And it may not be the same for Joe sitting next to you, whose circumstances are slightly different. And I think that also ties back to issues we've discussed previously, that choosing the right coating specification for your project, and not just one that is the latest hot off the press, good special price. You've got the specification. Neil, we've been talking about the risks of these highly negative pipelines in association with AC, and we're running out of time, but I am aware that there's another hidden danger, and that's the risk to the coating itself in the form of cathodic disbondment. So I'd love it if we
Yeah.
could reconvene tomorrow at 1 and take this discussion further, looking at some of the hidden dangers to coatings from cathodic protection. So right now, I just want to say thanks so much for joining us. And we do hope that you will be able to join us at 1 o'clock again tomorrow. You can use the same link, and we look forward to your joining us. Have a wonderful afternoon. Thank you.